Howdy folks, let's look at 7.4. I have four different PowerPoint documents for this particular section. I had to split it like that for some reason, maybe for the sake of efficiency. Not all of them are the same size though. Okay, cool. Without much further ado, let's get on with it. Definition. So by the way, this is about what's called partial fraction decomposition. Definition. It's a process by which a rational function, that is a ratio of polynomials, is written as the sum of simpler fractions. And the thing here is, do you remember from numbers what is called a proper fraction? If you have 3/4, that's a proper fraction. However, if you have 7/5, that's an improper fraction. What's the distinction? The distinction is, in the case of 3/4, the numerator is less than the denominator. That's what makes it proper fraction. Whereas 7/5 is improper because numerator is bigger than the denominator. Sort of similar thing happens even in case of rational functions. That is, if you have a polynomial n of x on the top and a polynomial d of x in the bottom, well, polynomials have degrees, right? For example, x squared plus 3x plus 4. Is that a polynomial? Yeah, polynomials are of that form. And what degree polynomial is it? Oh, second degree. Why is that? Because the highest power is x squared. Right, the highest power is 2 of the variable x, and so x squared being the biggest term, you say it is a second degree polynomial, right? And is 7 a polynomial? What? That's a trick question, man. Yeah, right. Is 7 a polynomial? Yes, it is. But what degree polynomial? A 0th degree polynomial. That's the idea. Yes, 7 is a polynomial. Anyway, so if we have a proper fraction like this, which means the degree of the top is less than the degree of the bottom, we could sometimes split that into partial fractions, and we will learn about how to do that. And the next thing is, what if it is not? What if f of x is not a proper fraction? It is an improper fraction. In that case, you perform a long division. You divide n of x, you divide d of x into n of x, and you get some quotient q of x. And that quotient q of x plus the, did I say n of x? Some r of x, I should have said. Here, well, n of x is the remainder of the remainder in the long division. Okay, so maybe some f of x is improper, and you can split like this, and that's what you need to do before you do anything. So we will now see how to find the partial fractions of a proper fraction. Partial fractions of a proper fraction. Boy, that's a mouthful. Okay, let's get on with it. Cool. Case 1. If the denominator d is a product of distinct linear factors. What? The denominator d of x is a product of distinct linear factors. First of all, linear, what is a factor? Factor, we call this as, these are the stuff in the denominator. Each one is called a factor because you got a whole bunch of things multiplying. So we have a first factor is p1x plus q1, the whole thing, and the second factor is p2x plus q2, that thing, and so on. So we have k factors here in the denominator. So because they are multiplying each other. Linear, are they linear factors? Yeah, if a polynomial is said to be linear if it is in the form of ax plus b, and p1x plus q1 is certainly of that form ax plus b. P1 and q1 are just numbers, constants. Cool. And what else? Distinct. Ooh, what distinct here means is that you're looking at none of them being equal. Like P1 and Q1 are not equal to P2 and Q2 respectively. So it's not like you have x plus 2 times x plus 2. No, you don't have that situation. If you have x plus 2 as one of the other one must be x plus 3 or x plus 4 or something else, right? So that's what we mean by distinct linear factors. Now, when it comes to partial fraction decomposition, if you were to have this situation where the denominator is comprised of distinct linear factors, this is the first step in the process. You set that equal to some constant a1 over the first factor, p1x plus q1, plus some other constant a2 over the second linear factor, and so on, all the way up to a sub k over pk x plus qk. Okay, what are a1, a2, ak? They are all unknown constants and we need to find them. We need to figure out exactly what the values of those constants are. That's the whole idea. Let me give a few examples. Do we have that situation? Do we have a rational function? Do we have a polynomial over polynomial? Yes, we do. Is the top a polynomial? Yes, it is. What degree polynomial? First degree. Is the bottom a polynomial? That doesn't look like a polynomial, man. Well, if you FOIL that out, would you get x squared plus x minus 2? Is x squared plus x minus 2 a polynomial? Yeah. What degree polynomial? Second degree polynomial. Do we have a proper fraction? Yes, we do. So we can now say, aha, because we have a proper rational function, we can write partial fractions of this, and especially recognizing that the denominator has distinct linear factors. X minus 1 is linear, x plus 2 is linear. So you tell me, what are we supposed to say? Some constant over the first factor, x minus 1, plus some other constant over x plus 2, which is what I wrote as a over x minus 1 plus b over x plus 2. Now if you say, how come, man, you got a1 and a2 and like that, how come you got ab? They are just arbitrary. So you want to call the first numerator as a sub 1 and the second numerator as a sub 2, be my guest. Okay, it doesn't almost matter what you call them as long as you make them different. Do not call this a and also call this as a. If you do, then you are forcing them to be equal, which need not be the case. Does that make sense? So as long as you're making them different, you call them alpha and beta, that's perfectly all right. Cool. Okay. The truth is, we need to figure out exactly what the values of a and b are. But right now, my focus is not on that. I want you to, there are 4 cases like this. We started with case 1, right? There are 4 cases. And I want you to get a perfect understanding of the moment you see something, what do you write as? That means when we saw this 3x plus 2 over x minus 1, this one, immediately we said, we should write that as a over x minus 1 plus b over x plus 2. How to figure out a and b? We will learn that later. That's what we are going to do now. Okay, I have another example. You tell me. Do we have a proper fraction? Yes, top is 0th degree, bottom is 3rd degree, and it's already in a factored form. So what would you say? Distinct linear factors? Yes. A over 2x minus 1 plus b over 3x minus 2 plus c over 4x minus 3. That's what you write as partial fractions of this. Cool? Beginning to get a hang of this? All right, let's get this. Provided the exact values, do Notice that the partial fractions we write are independent of the numerator. That's also provided the rational function is proper. So, that's something I needed to point out. Okay. Go back to the first problem. What if the top was to be, say, top were to be 4x plus 3 as opposed to 3x plus 2? What would you write here? It doesn't matter. You still say a over x minus 1 plus b over x plus 2. Get the idea? What if in the second problem the numerator was 4x squared plus 3x plus 7? Yeah, you would still do the same thing. A over 2x minus 1 plus b over all that. The only thing you need to worry about is this a proper fraction? When in the what I just said, I don't even remember what the hell I said. Some 4x squared plus 3x plus 7. Well, that's a second degree polynomial, and this bottom is a third degree polynomial, so that's a proper fraction. So we could say this. Okay, all right, let's move on. D of x is a product of linear factors, some of which repeat. Ooh. What in the world do we mean by that? Well, look at this situation. Okay, I'm asking you to focus on this n of x over p1x plus q1 to the k and the quantity p2x plus q2. So what's happening here? p1x plus q1 to the k. K is some kind of an integer, right? It's got to be an integer. 1, 2, 3, 4, rather a natural number. So in that case, we have a linear factor for sure, p1x plus q1, but it is repeating. Like if this were to be p1x plus q1 squared, then we are talking about the factor repeating twice. Whereas if it's a cube, we are talking about repeating 3 times, and so on. In those cases, the way you deal with that repeating factor is like this. You say a1 over p1x plus q1 plus a2 over p1x plus q1 the quantity square, and if it's repeating k times, plus a3 over the quantity cube, a4 over that, all the way up to a sub k over p1x plus q1 to the k. Cool? And then we also see this linear factor p2x plus q2. That is not repeating, so we'll call it as some constant b1 over p2x plus q2. Notice how none of these things is the same. a1, a2, a3, a4, all the way up to a sub k and b1. None of those constants is the same. We cannot assume them to be the same to begin with, is the point. It is entirely possible that after you evaluate them, they all come out to be the same. That's perfectly all right. We are not talking about that as a situation. But to begin with itself, you cannot assume they are all equal or some of them are equal. Cool? All right, let me ask you. Do we have this situation here? Is linear factor repeating? Good. Can you go ahead and guess as to what we should write as partial fractions? Especially keep in mind x minus 1 is repeating 3 times. So, would you agree we say a over x minus 1 plus b over x minus 1 square plus c over the quantity x minus 1 cube? Right? Does that take care of x minus 1, the quantity cube in the denominator? Yes. And also, there's a x plus 2, so we'll account for that by saying plus d over x plus 2. That's the idea. A over x minus 1 plus b over the quantity x minus 1 square plus c over the quantity x minus 1 cube and plus d over x plus 2, just like I said. Cool? All right. Answer this for me. A over 2x minus 1. I did everything in one shot. Okay. A over 2x minus 1 plus b over 3x minus 2 plus c over 3x minus 2 square plus, I lost track, a, b, c, yeah, d, e. So d over 4x minus 3 plus e over 4x minus 3, the quantity 4x minus 3 squared. Simple? Cool. All right. Can you factor x squared plus 5x plus 4? What do you think? Yeah, man, x squared plus 5x plus 4, that's equal to x plus 1 times x plus 4. Yep, you're right. Now let me ask you, can you factor x squared plus 5x plus 3? No, man. Yeah, like, in the previous case that x squared plus 5x plus 4, I know what to do. Like, what two numbers when multiplied you get 4, but when you add you get 5. 4 and 1, ta-da, that worked out. But like for the second one, nah, you cannot multiply two numbers and get 3, and when you add you get 5. You cannot. Really? I'm sorry to say, you're wrong. Yes, it is factorable. Didn't you know it's nothing but x minus negative 5 plus square root of 13 over 2 times x minus negative 5 minus square root of 13 over 2? Oh, come on. What? Yeah, I know. Where did I get this from? I got this from the quadratic formula. Could we find the roots of this quadratic, x squared plus 5x plus 3? Yeah. Can we use that quadratic formula, negative b plus or minus square root of b squared minus 4ac over 2a? When you do, you end up with this. So we should say x minus the first root, which is negative 5 plus square root of 13 over 2, times x minus the second root. That's what I did. So essentially, this is factorable. This x squared plus 5x plus 3. Of course, I agree. It's not as pretty as the previous one, but it is factorable. Okay? One more question. How about x squared plus 4x plus 5? I don't know, man. You just confuse the heck out of me. I want to say yes, I want to say no. I don't know. Okay, you tell me. Is that what you're saying? No, you cannot factor this. Dang. How do you know that, man? Well, here is the idea. So what does factoring a quadratic polynomial depend on? Ax squared plus bx plus c. Does anybody know the answer? It all depends on the D word. D as in David. DI. DIS. DISC. Yeah. Disc. Yeah. You got it. Discriminant, right? It all depends on the discriminant b square minus 4ac. If b square minus 4ac is greater than or equal to 0, then that quadratic is factorable, right? If b square minus 4ac is greater than or equal to 0, the quadratic is factorable. Otherwise, it's not. So let's look at x squared plus 5x plus 4. What is b in that case? 5. What is c in that case? 4. A is 1. So b square minus 4ac is positive 9, greater than or equal to 0. Greater than 0, clearly. Whereas x squared plus 5x plus 3, even for that case, we have b square minus 4ac to be positive 13, which is greater than 0. So they were both factorable. One was pretty, the other one was ugly, but definitely factorable. However, when you look at x squared plus 4x plus 5, b squared minus 4ac turns out to be negative 4. And that's why it was not factorable in terms of real numbers. Complex numbers, yes, but real numbers, no. And so, here is a definition. A quadratic polynomial is said to be reducible over reals if its roots are real, and is irreducible over reals if its roots are complex. So we are looking, when we talk about this partial fraction decomposition, whether a quadratic polynomial is reducible over reals or not. Okay. Now, case 3, that brings us to case 3. I needed to establish all that background because case 3 involves things like that. What if the denominator contained irreducible quadratic factors that are non-repeating, meaning there are no squares or cubes of quadratics themselves? Okay, what happens in that case? I'm saying, suppose you were to have a situation like this. Let's say p1x squared plus q1x plus r1 happens to be an irreducible quadratic. How do you account for that? You will say a1x plus b1 on the top over that irreducible quadratic polynomial. See that? You don't say a over, instead you say a1x plus b1 all over p1x squared plus q1x plus r1. That's how you account for the irreducible quadratic factor. And for this linear factor p2x plus q2, as before, simple a2 over p2x plus q2. Right? a1, a2, b1, they're all constants. Let me give solid examples. Cool. Look at the denominator. By the way, first of all, is it a polynomial? Yes. Top degree at the top, 1. Degree at the bottom, careful. When you FOIL out, would you get the highest term to be x to the 4? Yep, when you distribute. X to the 4 is the highest term, so 4th degree polynomial in the bottom. Cool. Is that a proper fraction? Yes, it is. So we can start thinking about writing partial fractions. X squared plus 4, is that a quadratic? Yes. Is that reducible over reals or irreducible over reals? What is A for x squared plus 4? What is A, B, and what are A, B, and C? A is 1, B is there is no x term, man. Well, I don't know what B is 0. If there is no x term, B is 0. The coefficient of x is 0. C is 4. So B square minus 4AC, 0 minus 4 times 4, 16, negative 16. So x squared plus 4 is irreducible. As simple as that. How about x squared plus 2x plus 2? Is that irreducible quadratic? B square is 4. 4AC is 8. 4 minus 8 is negative 4. Yep, that's also less than, that discriminant is also less than 0, negative. So both are irreducible quadratic factors. Okay, now the moment we realize that, how do we account for x squared plus 4, that irreducible x squared plus 4? We say ax plus b over x squared plus 4. Right? Now, what about this one? Yeah, similar. Cx plus d over the irreducible quadratic. Cool? All right. Next. Oh, that's it, huh? I think I got a problem later. Yeah, let's look at that. Fourth case. If d of x contains repeating irreducible quadratic factors, all I'm saying is go back to that same p1x squared plus q1x plus r1, but this time it's squared. Well, if you kind of intuitively, if you thought, hey, that's nothing but a1x plus b1 over p1x over this thing plus a2x plus b2 over the quantity square, yep, you are right. It's kind of like how it was for repeating linear factors, right? If we had something like a px plus q, the quantity square, we said a over px plus q plus b over px plus q, the quantity square, plus c over so on, like that. So same concept applies here. So let me give you an example. What do you think? We have x squared plus 4 is an irreducible quadratic factor, repeating twice. So let's make sure we say ax plus b over x squared plus 4 plus cx plus d over the quantity x squared plus 4 squared plus ex plus f over x squared plus 2x plus 2. Cool. So first you should be able to write things like this. And after you do, I think we can begin to work on the process. But I just want to test you. I taught 4 different cases. Now let's just run through a test. You tell me. Proper fraction? Yes. Linear factors in the denominator? Yes. Repeating? No. So, what is this? A over x minus 3 plus b over x plus 2. Is that what you said? If you did, awesome. You are absolutely right. Cool. Next. X minus 2 over x squared plus 4 times x plus 2. Ooh. What do we see? Proper fraction? Yes. X squared plus 4. Reducible or irreducible? Irreducible quadratic over reals. How do we account for that? Ax plus b over x squared plus 4. X plus 2, the quantity square. What do we call that? That's a repeating linear. So be careful. Account for x squared plus 4 with ax plus b over x squared plus 4. Account for this with a c over x plus 2 plus d over the quantity x plus 2 squared. Cool. Next. Proper? Yes. We have x squared minus 4. That's a quadratic. And is that irreducible? X squared minus 4. What? I tricked you. I hope you recognize that I was at least trying to trick you. Whether you fell for the trick or not, I don't know, but at least that was my attempt. Is x squared minus 4 irreducible? What is A? 1. What is B? 0. C? Negative 4. B square? 0 square is 0. Minus 4 times 1 times negative 4. Positive 16. Hey, that is factorable. Of course it is factorable. X squared minus 4. Isn't that in the form of a squared minus b squared, which is a plus b times a minus b? So couldn't we factor x squared minus 4 as x plus 2 times x minus 2? Yeah, so we better do that first, right? Not only should we do that, but we should also recognize that, dang, this x plus 2, and there is already an x plus 2, the quantity square. So the whole thing is actually cube. Oh. Cool. Once we see this, now things are straightforward. What do you say? A over x minus 2. Should that account for the first one? Second one, the x plus 2 the quantity cube. How do we account for that? B over x plus 2 plus c over the quantity x plus 2 square plus d over x plus 2 the quantity cube. Right? There we go. So that's how we account for that. Fourth. X squared plus 3x plus 4. Reducible or irreducible? B squared minus 4ac. 9 minus 16. Negative 7. Irreducible. And repeating. Also watch out for that. What do you say? Ax plus b over x squared plus 3x plus 4 plus cx plus d over the square of that. That should take care of that. Now x plus 2 the quantity square. We already used a, b, c, d, so we'll pick a e over x plus 2 plus f over the quantity x plus 2 squared. Right? You must develop an ability to write these things as quickly as possible. Everything has to make logical sense to you, and based on the logical sense and by being a little careful. Don't just rush into things and screw things up. Okay? you should be able to write this. Okay.